You are about to listen to the 365 Days of Astronomy podcast.
What do they talk about?
Astronomy, you know, stuff that's far away.
How far?
How far? Well,
This stuff is far. It's really far. This stuff is far, far, far away. We're talking far. Like uber far. You can't get there by car today. It's super duper crazy far, but not just pulsars, quasars, and stars. We mean it's far. Far, far, far. If there's some doubt, listen to a shout. This stuff is far.
the IYA 365 Days of Astronomy podcast starts now.
Hi again, and welcome to The Restless Universe, the podcast of the American Association of Variable Star Observers. You can find us on the web at www.aavso.org. I'm Mike Simonson, and with me today are Virginia Renahan and Rebecca Turner. Today we're going to talk about cataclysmic variable stars, CVs for short. Because hundreds of CVs get bright enough to study with even modest telescopes, and due to their unpredictability, they have become the favorite class of stars for many amateur variable star observers to follow. I have to confess, I've been waiting for this episode because I am a hopeless CV junkie. So let's dive right in and tell everyone exactly what cataclysmic variables are.
Of the roughly 4 billion stars in our galaxy, more than half occur in binary or multiple systems. Binary star systems come in many flavors. Red stars orbiting blue stars, huge stars orbiting tiny stars, black holes orbiting blue giants, and so on. In a CV binary, one star is a white dwarf, a collapsed star with the mass of the Sun squeezed into the volume of the Earth. The other star is a red dwarf, about the size of our Sun, but redder and less massive. This pair of stars is so close together that they orbit each other in just a few hours.
These are semi-detached binary stars where one of the components fills its Roche lobe and the other does not. We talked about this in the last episode about eclipsing binaries. The red star in a CV is so close to the white dwarf that it becomes tidally distorted, stretched out of shape. Gas is stripped off the red star and falls toward the white dwarf. Because of this conservation of angular momentum, the infalling gas can't stream directly onto the surface of the white dwarf. Instead, it forms a disk, an accretion disk, with the white dwarf at its center. The accretion disk usually outshines both the red star and the white dwarf in visible light.
If the white dwarf is strongly magnetic, other interesting things happen. We'll talk about that later.
CVs with accretion disks come in several flavors. The first to be discovered were the novae. Long ago, these stars were thought to be literally new stars. Novae stella means new stars, and that is why we call them novae today. They drew attention to themselves by their stupendous amplitude of variation, 6 to 19 magnitudes. You can imagine the ancient surprise when suddenly a bright star shone where there was none just the night before. The novae with the largest outburst amplitudes fade the fastest, so these are not long-lived visual events. But astronomers can follow the fading back down to pre-outburst levels for years.
Nova outbursts are due to thermonuclear runaways of the hydrogen-rich material that has accreted onto the white dwarf. Most novae known have only been observed to undergo one nova outburst, but several are recurrent novae.
Another group of CVs is the dwarf novae. Their outbursts aren't quite as spectacular as those of the novae, but the outbursts occur more often. In general, the more frequent the outburst, the smaller the amplitude of the outburst. For example, V1159 Orionis has outbursts every 4 days with an amplitude of about 2 magnitudes. On the other end of the scale, WZ Sagitti goes into outburst only once every 30 years, and the outburst amplitude is 7 or 8 magnitudes.
An interesting subset of the dwarf novae is the SU Ursa Majoris stars. They show 2 distinct kinds of outbursts, normal outbursts and super outbursts. Super outbursts can last 5 to 10 times longer and are slightly brighter than normal outbursts. Most dwarf novae exhibiting super outbursts have short orbital periods, less than 2 hours. Some of the SU Yuma stars with long outburst intervals, like WZ Sagitti, show interesting re-brightenings on the way back to quiescence after a super outburst. During a super outburst, an SU-UMA star shows an additional subtle modulation in the light curve called the superhump. This is caused by a wobbling or precession of the accretion disk. Superhumps show up in the light curve as a modulation with a period a few percent longer than the orbital period.
WZ Sagittae is now considered the prototype for a subset of SU-UMA class. A variety of SU-UMA stars in which the interval between super outbursts is measured in decades, while normal outbursts are few and far between. Other WZ Sagittae stars include AL Combe and EG Cancri, which have super outburst intervals of approximately 20 years. WZ Sagittae stars are the most inactive group of the SU-UMA type stars. The factor determining the different timescales between outbursts in dwarf novae appears to be mass transfer rate. WZ Sagittae stars have a very low mass transfer rate relative to other dwarf novae. Given the slow rate of mass transfer, it takes decades to accumulate enough material for a super outburst. One of the puzzling characteristics of these stars is why they show few or no normal outbursts during this time. Even with a low mass transfer rate, material should accumulate, drifting into the inner disk, triggering an outburst. But that doesn't happen, and we don't know why.
Z-Cam type stars also show cyclic outbursts, but they differ from normal dwarf novae by the fact that sometimes after an outburst they don't return to their normal quiescent magnitude. Instead, they get stuck about halfway down and may stay at that intermediate brightness for days or weeks before eventually falling off to minimum. The outburst amplitudes are generally from 2 to 5 magnitudes in V.
Another group of CVs with accretion disks are nova-like variables. The difference between the nova-like variables and the dwarf novae is that nova-like variables don't undergo dwarf nova outbursts. This is because the rate of transfer of matter in their disks is by and large stable. The overall brightness varies only slightly. In addition, the rate of mass transfer in the disks of nova-like variables is much higher than that in quiescent dwarf novae, so the accretion disks are very bright. Some nova-like variables show superhumps, like those seen in the SU-UMA stars. Unlike the super outbursting systems, however, these nova-likes have superhumps in their light curves all the time, so they're referred to as permanent superhumpers.
Magnetic CVs are systems where the white dwarf has an appreciable magnetic field, several tens of millions of Gauss. Because the matter in the accretion stream is partially ionized, it can't form a disk, because charged particles can't cross field lines. They can only spiral around them. Instead, the gas is threaded onto the field lines and plunges straight down onto the magnetic poles of the white dwarf. Copious X-ray and extreme ultraviolet emission is liberated at the poles. In some systems, the magnetic field of the white dwarf is strong enough to synchronize the rotation of the white dwarf with that of the red dwarf companion, much like the moon is locked to the Earth with the same face towards Earth at all times. These are the polars, or AM Hercules stars. The magnetic field in these stars is so strong, it's about 50 million times the strength of Earth's magnetic field, that no accretion disk can form.
In the intermediate polars, which have lower magnetic fields than the polars, the spin period of the white dwarf is shorter than the orbital period. The accretion process in the intermediate polars is through a disk with a disrupted inner radius, or an accretion stream as in the polars, or both.
Well, I can see why you love these stars, Mike. White dwarfs and red dwarfs whipping around each other with orbital periods of a few hours to 90 minutes, gases streaming from the secondary into a disk around the white dwarf, and of course the unpredictable outbursts. Dwarf novae are a lot of fun to watch, aren't they?
Absolutely. Visual observers can still contribute to science by watching and monitoring these stars, especially the ones that rarely go into outbursts, so they can notify astronomers with CCDs and big telescopes when something unusual is happening, sort of like fire spotters in the Forest Service. Amateurs with CCDs can take time series data and determine the orbital and superhump periods of newly discovered CVs and monitor faint CVs for flickering and strange behavior between outbursts. These are some pretty wild stars in our restless universe, and they are in no hurry to give up all their secrets, so there is much more to learn. Unfortunately, that's all we have time for today. From Rebecca, Virginia, and me, thank you for tuning into the Restless Universe, and we'll see you again next month. Goodbye.
You are listening to the IYA 365 Days of Astronomy podcast.